Okay, so now that we have the formulas there, we can start in our grids, we can start approximating the heat equation. So the heat equation, this is derivative, second derivative, and the grid for the heat equation is, we want to know what is u of I j plus 1 in terms of ui minus 1 j ui j and ui plus 1 j. In other words, if this is my point here, if I want to know the temperature at a particular point at one time step in the future, I need to know the temperature at this point, which is ui minus 1 comma j, the middle point, which is uij, and this point, which is ui plus 1j. Remember that the i's refer to going left and right. That's my x. J's are forward in time. So time is this way, and x is that way. Okay, and then we're going to use these formulas for this. Now remember that the heat equation is ut equals c squared uxx, where c is just some constant. So using the formula from above for this, we have that ut, the derivative should be u at, call it a b plus delta t, roughly, minus u of a b all over delta t. So that's the partial derivative of u expected t. X, a is some x coordinate, b is some time coordinate. We go a little bit further in delta t. And then uxx is this formula here. And remembering that u is a function of two variables, we want u at a plus delta x comma b, b is my time coordinate, minus 2 u of a comma b plus u at a minus delta x comma b, and I'll just be able to squeeze that in there, all over delta x squared. So in this case, if we're thinking about these kinds of notation, right, and we're thinking about a point I delta x, j delta t, what we get is ut equals c squared uxx. So ut would be u, let me write it down and then we will see why it works. So this is a time, this is a place at a, time b. So I delta x is a, j delta t is b. What we want to know is what's the temperature if we go forward one time step? So we're at a point A at a time j, and we want to go forward one time step to u to j plus 1, and we want to know the temperature at that point. And that should be equal to this term, right? So there's a delta x squared. And again, we're at this point, so we want I plus 1 comma j minus u of ij plus u of I minus 1 comma j. So this term, so let's think about this term. This term is the temperature at this point minus the temperature at this point divided by delta T. So Uij plus 1 minus Uij, because U is the temperature. This term, the Uxx term, is the temperature at the left plus the temperature at the right minus the temperature, twice the temperature at the middle, all divided by delta X squared. So this is the temperature on the right, temperature on the left, minus twice the temperature in the middle. And that gives us this. So we can solve this for this term is what we're interested in. We want to know the temperature one time step in the future. So Uij plus 1 equals what? Well, multiply both sides by delta T. And then I get Ui plus 1j minus Uij plus U, oh, there's a 2 on that, Uij, minus 2 Ui minus 1j. And then I bring this over, so a plus Uij. To simplify my life, I'm going to call this S. So I get Uij plus 1 equals S times all this stuff. So I'll have the S times Ui plus 1 comma j plus Ui minus 1 comma j. That's these two terms. And then I have minus 2s, that's this term, and a plus Uij. Note that this term and this term are the same. So that's plus 1 minus 2s Uij. And so that tells me how to get the temperature one time step in the future. So we're going to change our sharing now, and we'll go to Excel. So here is Excel spreadsheet, which I will be uploading to the E2L so you can see it. C, you can set C to be whatever you want. Delta X, you can set that to be whatever you want. Delta T, you can set that to be whatever you want. And then S is calculated as C squared delta X over delta T squared. So the yellow background here is my initial conditions. So we're thinking of this as being a bar of length, whatever length that is, from F to P, with initial temperatures, 0 at the ends, 7, 25, 50, 75, 25, 0, minus 30, minus 50, minus 10, 0. So it's cold here and hot there. And the red font, right, F and P, those are the boundary conditions, right? That tells you that you're keeping the ends of my bar at a temperature of 0. So X goes across, T is going down here, right? And we want to know what's the temperature as T goes on. So what we have to do is put in the update formula that we had, which was, you know, I don't know how much people have played with Excel, so this one will be a little bit lengthy just because I'm going to go through all the steps. So how do we enter things into Excel? If you want them to calculate something, you have to start with an equal sign. And our formula is, so equals S. And so you can just click on that, and that'll put in the B4. We have a little bit of a problem here in that we want every cell in here to have use the same value of S. So, oops. So we want to actually fix that. And the way Microsoft Excel does that, it says, put in a $sign before and after the B, right? And now S times, and that's shift 8, and it should be the one on the left, oops, earlier, plus the one on the right, one time step earlier, plus the quantity 1 minus 2 times S, and again, we click on that, And since we want to keep that reference fixed, we put some dollar signs there and we close the parentheses times the period directly before. And so that gives us our new temperature there. And then to fill in a row, we can just select this whole thing. So you select a cell and then you hold down the Shift key and select that entire range. And then Control R fills it to the right with the same formula. And so what that did is when we look at this cell, for example, if you click up in the top, it'll tell you what it depends on. The B4s tell you it depends on S, and this depends on G1 and I1 and H1, right? The three cells above. And same thing for this. This depends on S, and it depends on S because we put in the dollar signs for S, and then you've got the three above. Great. So now we want to fill in our entire bar. So if I can get this thing to scroll down, which it's not wanting to do, I've got about 200 time steps in here, and we just hit, you click, so same thing, right? You click on one cell, and then you click at the other end, shift click, and that makes the whole thing gray, and then Control D to fill it all down with the same formula. Oh, except it did this stupid thing. It does that sometimes. Okay, so let's try this again. Click there in this one cell, and then go down to the bottom cell that you want, shift click, and then Control D, and it fills everything in. And so there's our temperature, right? You can see, we won't go into too much detail, but you can see that this part, it's 0 at one side, but 25, 50, 75. So to the left of this point, no, to the right of this point, it's pretty hot. So heat is going to be flowing through this point, so it gets hotter. 75 is the hottest place. Its heat is going to be shed this way and that way. And so it gets cooler. This gets a little bit hotter, but this one is sending heat that way into here. This minus 50 is colder than the minus 10, so it's actually going to draw heat from the minus 10, so that becomes a minus 13. And so you can see how that works. So one nice thing that you can do with Excel, if we take this big batch of data and go back up, we can insert charts. And its recommended chart is that, which isn't very interesting. But what's much more interesting is the surface chart. And we can move this over here somewhere, and then we'll scroll over to look at the surface chart. We'll make this a lot bigger. There. So there's our surface chart. So what is this looking at? This is the heat temperature. This is the temperature as a function of time. So this axis running out to the right, that's our time steps. The vertical axis is the temperature of this thing. You can see that there's a very cold temperature here, very hot temperature here, and it pretty quickly, right, the temperature pretty quickly settles down between 0 and 20. If you look down here at the bottom where the legend is, you can see that this yellow part is where the temperature is between 0 and 20, right, and the temperatures die out pretty quickly. If you right click on this, you can pull up something called 3D rotation, which means that you can rotate this around a little bit. You can see what the temperature does. Here's our cold place. It, you know, by the time we get to what, 60 almost, it has heated up to above 0, and then the temperature here and everything is going down to 0. So you can rotate in a variety of ways. But if we look at our data, right, by the 39th time step, all the temperatures are almost between 0 and 20. We just have a couple of very low temperatures there. And then by the 50th time step, all the temperatures are between 0 and 20. And so the bar is dissipating heat pretty quickly out through its two edges. You can tinker with delta X and delta T and S. If we make delta T equal to, so remember what we've got here is 200 time steps. So if delta T is 0.1, that means our time step now is 200 of that is like 20 seconds. So if we make it 0.01 and just see what happens over the first, well, actually, we want to get down to within 10 seconds was what, like 50? Yeah, 51. So if we just want that, first 0.051 seconds, cut that in fourth, say 0.025. 0.25. Right? And then that gives us all those numbers, and that gets us up to about 200 times half a second. So, and that gives us sort of the first bit of that longer graph we had, and now you can see that it, go back to our 3D rotation. Right, now you can see a little bit more detail because we shortened the time frame. So you can get bits and pieces of this graph by shortening the time frame or by lengthening the time frame. One of the problems if you lengthen the time frame too much, though, suppose we say delta T equals 1, and that'll change all the numbers. Equals 1. And we actually, it becomes unstable and it blows up. And our graph is very unhappy there. So there's only a limited number of values that you can get actual convergence for. 0.01, for example, 0.01, right? And this would be 200, 2 seconds maybe. And the first 2 seconds we get down to, well, still some is a little bit hot, but not too bad. And you get that graph. Okay, so we can, here's the same thing, but I changed the boundary to be 50. Right, so here we have one side is held at 1, at 0, one side is held at 50, and you can see that the temperature is going up on the side that's at 50 degrees, and but it's decreasing from above, from where it was over at 75, and getting hotter there too. So if we rotate this around, you can see a little bit about what the temperature is doing. We can look for a longer time period by changing delta T to say 0.1, and that changes all our numbers. And over a long time period, this is what you get. And this is sort of what we expect here at the end, right? Because when we looked at the heat equation, you should get a steady state heat equation. If your ends are held at 0 and 50, you should get a line from 0 to 50. And so the heat distribution ends up being just that line from 0 to 50. So that's one way to put together a heat equation. You can do various things here, right? You can change the boundary conditions to be some function of T if you want, and you can track how the surface changes. One nice thing about numerical analysis is that you don't really have to worry too much about the boundary conditions. You just plug in various things for the red numbers, and that tells you it'll automatically adjust to fit that. Okay, so that's the heat equation.